In this section, we will be looking at rates and proportions. We're actually going to be looking at proportions and then rates. I should switch my titles. Anyways. So a ratio compares quantities by division. So an example of this, if a group contains 60 women and 30 men, then the ratio of men to women would be 30/60 or 1/2. We always write our ratios in lowest terms. A proportion is a statement that says that two ratios are equal. And we can use proportions to solve for missing values using the cross product principle for proportions. This states that if you have two proportions, one that says A/B, and that's equal to C/D. So I have two ratios that are equal to each other, so therefore it's a proportion. I can use what's called the cross product principle, where I multiply A times D and B times C. So A times D is equal to B times C. And then I can solve if one of these values is unknown. So the cross product principle for proportions. If A/B is equal to C/D, then, I'm missing the word then, A times D is equal to B times C. So a few examples with a missing value, 10/x equals 2/3. So I'm going to use cross products to solve for the missing value. So I'm going to multiply across. So 10 times 3 equals x times 2. 10 times 3 is 30. I'm going to rewrite the right-hand side as 2x because it just looks better. I can solve the right-hand side for x by itself by dividing by 2. Whatever you do to one side, you have to do to the other. So now x is by itself, and it equals 15. And then we can check. So 10/15 equals 2/3. The easiest way to check this is to just plug it into your calculator. 10 divided by 15 is 0.6666666666. 2 divided by 3 is 0.66666666. I get the same number in my calculator for both of those ratios. That's the quickest, easiest way to check to make sure that these are correct, is take each ratio on its own, plug it in your calculator, make sure you get the same answer. So the second one, 24/x equals 12/7. I'm going to do the same thing, but I'm going to do a different color. So 24 times 7, and we'll do x times 12. Write that out. 24 times 7 is 168. And I'm just going to write 12x because it looks prettier. I can get the x by itself by dividing both sides by 12. And 168 divided by 12 is 14. So 24/14 equals 12/7. And when we plug those into the calculator, we get the same exact number. Not just similar, not close, exactly the same number in the calculator. And then the last one here, totally fine that we have a negative. So I'm going to cross multiply. So negative 3 times x equals 8 times 6. I'm going to write negative 3x equals 48. Yes, I had to do 8 times 6 in my calculator. I was never good at my 8 times tables. So that was 48. I want to get the x by itself. So I'm going to divide both sides by negative 3. Because if I divide by just 3, then I'll still have a negative on that x. That's not what I want. So x equals negative 16. And then we can check that by making sure we get the same fraction in our calculator. Negative 3 over 8 equals 6 over negative 16. Since there's one negative in the first fraction or in the first ratio, there should be one negative number in the second ratio. And we do have that. So that is good. So those are some basic examples of proportions. It's just a straightforward proportion. But another thing that we can do with proportions is we can use them in word problems, in applications. So here's one application. An object's weight on the moon is proportional. Ooh, that's a fun word. That might be important. I'm just going to circle that now. To its weight on Earth. Neil Armstrong weighed 360 pounds on Earth when he had all of his equipment on, and 60 pounds on the moon with all that same equipment on. What is the moon weight of a person who weighs 186 pounds on Earth? So we're going to use proportions because of that keyword proportional to solve this problem. So we know that Neil Armstrong weighed 360 pounds on Earth and 60 pounds on the moon. And we have this other person who weighs 186 pounds on Earth, and we want to know, what do they weigh on the moon? What is their moon weight? There are a couple of different ways that you can set up this proportion. The most important thing to remember when you are setting up these proportions is you have to be consistent. And what I mean by that is I'm going to set up my proportions by putting the earth weight over the moon weight. I need to do that for both of my ratios. So my first ratio is going to be for Neil. So Neil's earth weight was 360 over his moon weight of 60. And that's equal to this other person that I have. So I need to be consistent now, and I need to put the earth weight of this other person on top. So their earth weight is 186, and their moon weight is what we don't know, what we're trying to find. So that needs to go on bottom, and I'm going to represent that with an X. You could also set up this proportion by doing Neil over the person and doing a ratio for Earth weights equal to moon weights. Totally fine. It will get you the same answer. But you have to be consistent. If you decide I'm going to put Neil's weights on top, then they have to be on top for both of those ratios. And the other person has to be the numbers on the bottom. However you decide to set up your ratios, you have to be consistent. You can't change the second one up because you say, oh, I don't want to have X in the denominator. That makes me nervous. Too bad. That's how you decided to set it up. So now that I have my ratio set up, my proportions set up, I can cross multiply. I get 360 times X equals 60 times 186. So 60 times 186. So I'm just rewriting this side so it looks better. And then the right-hand side becomes 11,160. And then we want to get the right-hand side. Nope, I'm sorry, the left-hand side. We want to get that X by itself. So divide both sides by 360 and we get 31. And we do have units on this now because it's an application. So 31 pounds. So based on this, if you weigh 186 pounds and you go to the moon, because of the change in gravity and all of that stuff, your weight on the moon will only be 31 pounds because there's less gravitational pull. You don't need to know that, and I don't even know if that's right. I'm a math teacher, not a science teacher, but that sounds right. So there's one example. Let's do another one. To estimate the number of bass in a lake, wildlife biologists tagged 50 bass and released them in the lake. Later, they netted 100 bass and found that 27 of them were tagged. Approximately how many bass are in the lake? So this is what they actually do to one of the ways that they actually estimate wildlife populations is they will tag some of them, let them out, and then take a sample later, and based on how many of them are tagged from that sample, they'll use proportions to figure out what is the population size of that species. There are other reasons why they tag, but this is one of the reasons why they do that. So initially they tagged 50 bass, and then later they netted 108, and 27 of them were tagged. So again, I'm going to set up my two ratios to create my proportion. I just want to make sure that I am consistent. So I'm going to set this up as tagged over total. This is how I'm setting it up. Yours could be set up slightly different. And then I'm going to do the initial equals maybe the second, because they had their initial tag, the initial pull when they tagged everyone, and then they went back and they did it later, like the second time. So that's how I'm going to set up my two ratios. So in their initial one, they had 50 tagged out of an unknown total. That's what we're trying to figure out. And then when they went back later, they found 27 tagged out of the 108 that they netted. So out of the 108 total that they were looking at. So using my Cross products. 50 times 108 equals 27 times x, or x times 27. We get 5,400 equals 27x. We can solve for x by dividing both sides by 27. We get 200 equals x, and that's 200 bass. So there are 200 bass in this lake. So one more example. The property tax on a house with an assessed value of $250,000 is $3,500. Determine the property tax on a house with an assessed value of $420,000, assuming the same tax rate. So the value of the house is $250,000, and they have to pay $3,500 in taxes. We want to know what is the tax if the house has a value of $420,000. So I'm going to do tax over value. I'll do house 1 equals house 2. So house 1 is 3,500 over 250,000. House 2 is an unknown amount in taxes over 420,000. These are going to be fun numbers. So 3,500 times 420,000 equals 250,000 times x. Oh my goodness, 147 with 7 zeros. And then divide both sides by 250,000, just 250,000. And the unit on this is dollars. So $5,880 is what the property taxes would be if we assume that these two houses would have the same tax rate. Which that's a pretty big assumption, but it's what the problem says. So 3 different examples of how to do proportions with word problems. The most important thing is just establish how you're going to set up the proportion once you have determined what it is that you have and what it is that you maybe are missing, and make sure you are consistent. If you start moving things around and flipping fractions around and stuff like that, you're not going to get the correct answer. So one last thing in this section are unit rates. So a unit rate is a unit meaning one of something, or it is a ratio with the denominator of 1. So the most common place that we see unit rates are when we're looking at like the cost per something, the price per something. So I have one example where we're going to look at that. So a grocery store is selling 2 different size jars of Skippy peanut butter. They have a 16.3 ounce jar for $2.99 and a 64 ounce jar for $10.99. Which size jar of peanut butter is the better deal? Fun fact, I did actually go to a grocery store website to find this information. This is real data. So let's find out which size jar of Skippy peanut butter should I have bought at the store. So the way that we're going to find this is we're going to find the unit rate or the unit price for each jar of peanut butter. And I'm going to find that by taking, let me start writing, hang on. I'm going to find the unit price, and I'm going to find that by taking the price and dividing that by the size of the jar. You can also do this with pizza, looking at the price divided by the size of the pizza. You can do this with cereal, you can do this with tires, you can do this, anything that has a price and different sizes associated with it. You can figure out a unit price to it to figure out which one is the one that you should be buying. So I'm going to start with the smaller jar. So the price of the smaller jar is $2.99, and it is a 16.3 ounce jar. So I want to know how much is it for each ounce of peanut butter. That's what this is going to tell me. So $2.99 divided by 16.3, 0.183. I'm going to go to 3 decimals just in case I need to make the comparison after I do the larger jar. So it's going to cost me roughly 18 cents for every ounce. So maybe like 18 cents per tablespoon. Maybe a tablespoon is roughly an ounce. I don't know. But I'm going to guess. Okay, and 18 cents per tablespoon of peanut butter for the smaller jar. So now let's look at the larger jar and compare. So the larger jar is $10.99, but I'm going to get 64 ounces out of it. So $10.99 divided by 64, 0.172 per ounce. So each ounce is going to cost 17 cents. If you think about an ounce is roughly a tablespoon, 17 cents per tablespoon, if that's the correct comparison. So which size jar of peanut butter is the better deal? The larger jar because the price per ounce is lower. And you may be thinking, well, duh, it's always better to buy the larger size. That is not the case, especially at a particular blue retailer, I'll just say it, at Walmart. Okay, Walmart likes to play this game where the larger items are not the better unit price. So it's very important to know how to calculate this because they like to make you think that the bigger jar is going to be the better deal, but it's actually not always the case. And I've noticed that particularly at Walmart, it could be true at other places as well. It was not true at this grocery store for their peanut butter. So that is how you calculate a unit price. You take the price divided by the size, and you compare. The better deal is always going to be the one with the lower price per whatever the unit is of the item in question. So this was in ounces, so that's why it was price per ounce. If we were looking at something in terms of feet, okay, maybe we're looking at a fruit by the foot. I've got food on the mind. Then this would have been a price per foot. So just keep that in mind as you're working through those. And that's it for this section.